In this video, we are going to have a look at the most commonly used protein language models, including the ESM1B transformer network, where ESM stands for Evolutionary Scale Modeling. We will shortly look at its model architecture, the training process, and for what the trained model can be used. And at the end of this video, we will also have a look at alternative protein language models, including the successor of the ESM1B model. The ESM1B transformer network is an open source protein language model that was published by Rives et al., who are part of the Facebook AI research team in the journal PNAS in 2021. The architecture of the model is a transformer network encoder, which you have seen in the previous videos. And the model was trained for the training task that you've also seen before, the prediction of amino acids that were masked in the input sequence. We will have now a closer look at the exact architecture and training of this model on the following slides. Let's start by looking at how the ESM1B model handles the positional encoding and the token embeddings. In contrast to what we have considered so far, the ESM1B model uses learned embeddings for all possible amino acids or tokens. These embeddings have a dimension of 1280, which is also the dimension of all token representations in the model. This is the variable that we named D in the previous videos. For the positional encodings, the authors tested both learned representations and also the predefined sinusoidal positional encodings, but they found that learned positional encodings led to better results. As you know, the positional encodings need to have the same dimension as the token dimension, so they are also vectors of dimension 1280. But how can we actually learn token and positional embeddings? I put positional in brackets here because I'm going to show an example for token embeddings, but the principle is the same for positional encodings. What we learn during training is basically the entries of a matrix, where each row is the embedding of a specific amino acid or token. In this case, we would have one row or one vector for each token that can be the input of the model. Additionally to the 20 tokens for the 20 amino acids, we could have one padding token that we can use to ensure that all sequences of a batch have the same input size. We could have one token that represents a masked amino acid and also one token for unknown amino acids within a sequence. And later, when training the model for supervised tasks, we will see that we will also have a so-called classification token for capturing information about the whole protein sequence. But for now, let's assume we have 23 different tokens that we want to encode. When applying the model, we can access each token representation quite easily by encoding the type of token in a binary vector. Let's say we have the second amino acid at a certain position, so we generate a vector with all zeros and a single one at the second position. If we multiply our embedding matrix with this vector, this results in a single vector that has in its columns the entries of the second row of the representation matrix. So this is our embedding for this token. And since all entries of the matrix can be adjusted or learned during training, we have learnable embeddings. This works very similar for the positional encodings. Instead of having 23 rows, the number of rows depends on the maximum sequence length that is allowed. And in the case of the ESM1B model, the maximum sequence length was set to 1024. So we would have a 1024 by 1280 dimensional matrix that stores the learnable positional encodings, and we would also encode the different positions of an input sequence in a binary one-hot encoded vector to access the different positional embeddings. The architecture of the ESM1B model is, with a few small exceptions, identical to the encoder that we have seen in the previous slides or in the previous videos. As we have already seen on the last slide, the representation dimension of the encoder is equal to 1280. The number of attention heads in each multi-head attention block was set to 20. And we know that in order to get the representation dimension of each attention head, we need to divide the total dimension d by 20, which is equal to 64. So the dimension of each attention head is actually quite small. The maximum sequence length is set to 1024. And since most protein sequences have a shorter sequence length, this is not a problem in most cases. However, the model was not trained or was only trained to learn positional embeddings for the first 1024 positions. So if we want to apply the model to longer sequences after training, we can't apply the model to the full sequence because we simply have no way of encoding positions over 1024. So what you would typically do is you would simply use the first 1024 amino acids in the sequence and omit the rest of the sequence. The hidden dimension of the feed-forward neural network was set to 4 times the size of the dimension d, which is equal to 5120. In the ESM1B model, there's a total of 33 such encoder layers, which results in a total number of 652 million learnable parameters. And as I said, the architecture is mostly identical to the encoder we've seen before, with a few exceptions. One such exception is that they applied the layer normalization before the attention block and before the feed-forward block, instead of applying it afterwards, because they found that this slightly improves model performance, but this didn't affect overall performance that much. Another small difference is that they used in the feed-forward block a GELU activation function instead of a ReLU activation function. As you know, the ReLU function is 0 for negative values and leaves positive values unchanged. The GELU function is very similar, but as you can see in this image, it also returns small negative values for small negative input values, which means that this function provides a smoother output compared to ReLU for values that are close to 0. This model was trained for the mass token prediction task, and similar to what we have seen before, they have selected randomly 15% of the input tokens, which they want to predict with the model. However, instead of replacing all of these tokens with the same mass token, they only replaced 80% with the mass token. 10% of the selected tokens were replaced with a random amino acid, and the remaining 10% were left unchanged. And even if not all of the selected tokens were masked, they still trained the model to predict the true amino acid type for all of those tokens. This approach was compared to the approach where all of the selected tokens were masked, and it was found that using this approach led to slightly better results, but the difference was not very big. As a dataset, they used the UniRef50 dataset. This dataset is based on the UniProt database, which stores a total of 250 million protein sequences. The UniRef50 dataset is a group dataset which groups sequences that have sequence identities over 50%, and then from each of those groups, only one representative sequence is selected, which results in a dataset of approximately 30 million diverse protein sequences. And finally, regarding the training times and computational resources, the model was trained for almost 20 days simultaneously on 64 large GPUs. Each epoch, which means seeing each of the 30 million protein sequences once, was completed in 8.5 hours, and in total the model was trained for 56 epochs. So let's see if the model actually learned representations that store useful and meaningful information. On the one hand, the authors tested if the model learned structural information from seeing only the linear amino acid sequence and having no information about the folded 3D structure of the protein. On this slide, you can see a contact map for a protein that shows which amino acids are close to each other in the folded 3D structure of the protein. On the X and Y axes, we have the amino acids numbered as they appear in the protein amino acid sequence. So this is a protein with a little bit over 300 amino acids in its sequence, and the black dots indicate if two amino acids are close to each other. You see this black diagonal line because obviously each amino acid is close to itself and to the amino acids next to each other. But you can also see points like these, where, for example, amino acid number 50 is close to amino acid number 250 in the 3D structure of the protein. We can now use the learned amino acid representations of the ESM1B model to predict for two amino acids if they are close to each other. In this case, we would not calculate the element-wise mean over all amino acid representations to get a whole protein representation, but instead we would use the amino acid representations themselves. If we can successfully use the amino acid representations for this task, this shows that they also store structural information. This can be formulated as a binary prediction problem, where we want to predict for all pairs of amino acid representations I and J, where I and J are the positions in the protein sequence, if those two amino acids are closer than a certain threshold to each other or not. In the ESM1B paper, this was done by first calculating a linear transformation of HI, the representation of the amino acid at position I, and HJ, the amino acid representation at position J, by multiplying these matrices by matrices P and Q. Then we can calculate the scalar product of both new vectors, which results in a single value. Then we can add a constant value b and apply the sigmoid function, which results in a value between 0 and 1, where we can interpret all values above 0.5 as positive, which means being close to each other, and we can interpret all other values below 0.5 as negative predictions. The parameters of the matrices P and Q and the value b are learned during the training process for this prediction task. And it is indeed possible to predict the entries of such contact maps reasonably well using the ESM1B amino acid representations, showing that they store structural information. On the previous slide, we have seen that the ESM1B model generates representations that store structural information. But how about the function? Can we use the learned representations to predict the functions of proteins? Since we already know that protein structure determines the function of a protein, it is likely that we can do this. And indeed, ESM1B vectors have been used successfully for a wide variety of different protein prediction tasks. Here we are considering the whole protein ESM1B vector again, which is the element-wise mean of all amino acid representations. For example, these vectors have been used to predict the functions of enzymes. There are hundreds of different classes of enzymes that all catalyze different chemical reactions. And we can use the ESM1B vectors to predict to which class an enzyme belongs. Or we can use these vectors to predict which substrates transport proteins can transport across a membrane, or we can predict protein-protein interactions, or if a certain drug is inhibiting the function of a protein. This shows that the ESM1B vectors indeed store a lot of useful information regarding protein function. To make these protein function predictions, we would calculate the ESM1B vectors that we call vector E here for all proteins that we want to make a prediction. Then we would train a separate machine learning model, for example, a linear regression or logistic regression model or fully connected neural network or gradient boosting model to predict the property or function of interest. And in my experience, gradient boosting models typically result in best model performance among these models when applied to ESM1B vectors for protein function or property prediction. If you want to use the trained model and get either the amino acid representations or the average mean representation of the ESM1B model, you can use the Python package fair-ESM. You can install this package by using pip install fair-ESM. And here I'm using an older version, 0.4 of this package, but the newer version should work as well. We then need to load the trained ESM1B model. And if you do this for the first time, the model will be downloaded from the internet, which can take a few minutes. We also load the batch converter that converts an amino acid sequence into the input tokens for the model. Okay, so let's look at an example for calculating ESM1B vectors for protein amino acid sequence. Here I use the protein amino acid sequence with 371 amino acids as an input. And we use the batch converter to get the input tokens for these proteins. Then we calculate all ESM1B representations for these proteins. And since we want to get the amino acid representations from the last layer, you can see here that we access the representations from the 33rd layer. Now we want to take the element-wise mean of all amino acid representations. The first token is a special token, so we do not use that, but we start at position 1 and go up to position 372, and we take the mean across those representations. And you can see that this results in a 1280 dimensional vector. If you want to have the representations for each amino acid from the last layer, you would simply not calculate the mean. We will now look at two additional and alternative protein language models to give you a broader picture of what kind of pre-trained protein language models exist. The first one is ESM2, which is the successor of the ESM1B model. ESM2 is actually a family of many different protein language models that distinguish from each other by having different model sizes and hence different numbers of learnable parameters. The number of model parameters range from 8 million to 15 billion, and for comparison, the ESM1B model has 652 million trainable parameters. The models with higher number of parameters show better performance results, and the ESM2 with the same number of parameters as the ESM1B slightly outperforms the ESM1B model. So what is the difference? ESM2 is, as well as the ESM1B model, a transformer network encoder that was trained for the masked language modeling task. In the manuscript, the authors claim that the improvements in model performance result from the following points. The first one is improved training data. Instead of training the model on approximately 30 million different protein sequences, such as the ESM1B model, the model was trained on approximately 65 million unique sequences. The next one is model architecture. As I said, the model architecture is basically the same as the encoder used for the ESM1B model that we have seen, only the number of layers, number of attention heads, and hidden dimensions differ. The only real difference, besides model size, is that ESM2 uses different positional encodings called rope instead of learned positional embeddings. However, as the authors state in their paper, for larger ESM2 models, there's no real improvement compared to the predefined sinusoidal positional encodings. And the ESM1B model did have dropout in the attention layers and the feed-forward block, but since they found out that this doesn't have any effect, they removed dropout to free more capacity. And lastly, it is stated that improved computational resources were used. However, in the manuscript, I couldn't find any details on which and how many GPUs the model was trained. So in summary, I think we can say that the improvements mostly result from a larger training data set, larger model architecture, and more computational resources, and not necessarily from a new or advanced model architecture. Another popular protein language model is the ProtT5 model, and there exist multiple ProtT5 models that were presented in the same paper, but I'm going to discuss only the model showing the best performance, which is named ProtT5XLU50. The training task of this model is very similar to the training task of the ESM models. 15% of the amino acids of the input sequence were randomly masked, and the model was trained to predict the type of the masked amino acids. Also, the training data is very similar. PROT-T5 was trained on the UniRare50 dataset, which contains approximately 45 million unique protein sequences. And the biggest difference compared to the ESM models is the model architecture, which is a so-called T5 transformer network. This T5 transformer network is highly similar to the transformer networks that we looked at so far in this lecture, but consisting of an encoder and a decoder. We have seen that for encoding protein amino acid sequences, in principle, we do not need a decoder. However, here a decoder was used nevertheless in order to better solve the mass token prediction task. However, after model training, the authors found that the best protein representations were generated only using the encoder and omitting the decoder. So the model architecture for generating representations is very similar to the ESM models, but the architecture during training differs. And the PROT-T5XLU50 had a total number of approximately 3 billion learnable parameters, including the encoder and decoder parameters. And finally, we see here a table comparing the models that we've discussed in this video for different prediction tasks. The perplexity states how well the model performs for the masked language modeling task that is used for model training. The tasks denoted by LR show how well long-range contacts between residues or amino acids can be inferred from the attention maps, and CASP and Camero refer to tasks that use the learned representations for protein structure prediction. The CARP model that you see at the bottom of the table is, in contrast to all other models, a model that is based on convolutional neural networks instead of a transformer network. And you can see that if you compare this model with transformer networks of comparable number of parameters, CARP performs a little bit worse, but is not too far away from the performance of the transformer-based models.